In the last lecture, we learned about Stein's unbiased risk estimator. Using a Stein's unbiased risk estimator, we can derive a formula to know what the optimal number of bases are for RBF network. Also, using a Stein's unbiased risk estimator, we learned more about overfitting and complexity control. We learned why the behavior of true error set and empirical error set has this characteristic that empirical error always goes down and true error goes down up to some point and then start going up. We also learned some justification behind cross-validation technique. So the form of sure, if you remember, was that true error was empirical error minus a constant plus a term such that this term depends on the complexity of the model. So that was derivative of the estimated model with respect to one of the data points. Means when I change one of the data points, how the model will change. So the more complex the model is, this quantity is going to be larger, right? So if you have a line, it's smaller than a high dimensional. A high polynomial with high degree. So it becomes larger when the complexity of the model is large. So this error, this empirical error, as we learned, goes down always, but this true error has this behavior, and we need to optimize this one, which we don't have it usually unless we estimate it. But this is easy to compute. You can compute usually, the training error. It's easy to compute. Okay, one way to avoid overfitting is regularization. So regularization is a general name for a class of techniques to avoid overfitting in any learning algorithm, any machine learning algorithm. But using the formula of Schur, Stein's unbiased risk estimator, again, you can get some insight about regularization. See here, this is constant. As far as I want to minimize this, this has no effect. You can see that this is empirical error which goes down, plus a term which has to do with the complexity of the model. So when complexity of the model get larger and larger, this is complexity. This value goes down and down, but this value goes up. So and at some point it becomes dominant, so it makes the whole curve going up. So what you need to have in mind is that the last part, the last term, is a term which has to do with the complexity of the model. So the idea of regularization is to add a term to empirical error, which will increase by the complexity of the model. In the case of Schur, we compute it exactly. So we know what the bias is. So we compute it exactly. But in many cases, it's pretty hard to compute. In RBF, you can compute it, but in a complex neural network, you can't. So in general, it's pretty hard to compute this derivative. So I can just add not this term, a term, which has to do with the complexity of the model. When the complexity goes up, it goes up. Okay, that's the idea of regularization. Okay, the setting now is that I have a function, estimated function f hat, and I have some parameter in the model. Let's call it theta. And say I have an error function, objective function. In general, this error function is a function of input x, target variable y, and the parameters of the model, which is called theta. So regularization means adding a function over theta, like this function. And this function is increasing function with respect to the complexity of the model. When complexity is larger, this part becomes larger. It's like this term, but here we don't have any estimation of this term. So this could be many different things. This last part could be many different things, this regularizer. Most common regularizer is L2 norm of the parameter. So basically, you want to make sure that the parameters of the model doesn't get large. The parameters of the model is small, okay? So in terms of neural network, I mean, you can apply it in anywhere. You know, if you have a least square regression, for example, you can add L2 norm to this. Do you know what is the name of that? Ridge regression, right? You can add L2 norm to that. It's called ridge regression. In terms of neural network, it's called weight decay. So you add L2 norm, and it's called weight decay. So if you remember, in neural network, we had a weight, and through the process of gradient descent, we wanted to update this weight. So the new weight was the old weight minus some learning rate derivative of the error with respect to this weight. That was our update, right? In gradient descent or stochastic gradient descent. Now, what we do here is to add a penalty function to our error function. So I have this error function. I add a penalty function. And this penalty function in weight decay is simply norm 2. Okay, L2 norm. So L2 norm basically is Uij squared for all ing. So I can add 1/2 here, because when I take derivative, you know, this 2 and 1/2 will cancel, and I can add a coefficient here as, okay. So that's my new objective function, which I call it regularized error instead of error. So now, instead of minimizing the empirical function, which always goes down, I'm going to minimize this regularized error function. See, the last term has an effect like this one. Okay? So with complexity, it goes up. So I don't minimize this. I will minimize this. At some point, this becomes dominant, and the curve starts to go up. So my basically update would be Uij minus rho. Now derivative of regularized error with respect to Uij. So this Uij will be Uij minus rho. Derivative of regularized with respect to Uij, which is derivative of the first term with respect to Uij, which I can compute using backpropagation, similar to what I did before. But I have additional term plus derivative of this with respect to Uij, which is going to be 2 Uij. This 2 will be canceled with this one. So it's just alpha Uij. So everything is similar to the update formula that we had before, except that I'm going to add alpha times uij to this before subtracting this from uij. This is called weight decay. It doesn't let weights to get so large. Okay, you may wonder what weight has to do with the complexity of the neural network. Because we know if I add nodes to neural network, it becomes more complex. If I add layers, it becomes more complex. By why large weights make a neural networks more complex compared to small weights? Any idea?
If it's too small, it can just be one bit.
Let me give you a hint. In many cases, the nonlinearity that we use at the end of each unit has this form. This is 0. So large weights are here, here. Small weights are here. Any idea that why large weights makes the model more complex? Yes?
So you get more often, you get zeros and ones instead of in between, values in between that.
You mean in the output?
Yeah.
So what's wrong of getting 1 instead of getting 0?
Or you're getting ones instead of 0.5.
Mm-hmm. So when we are talking about complex model, basically we are talking about nonlinear model. Okay? So simple model, linear model. Complex model, nonlinear model. But the more the nonlinearity you have in a model, the more complex the model is. So if weights are small, close to 0, the active part of this nonlinearity function is this part, which is almost a linear function, right? As if at the end of each unit you have a linear function. When weights are larger, it starts to behave nonlinear. So large weights contributes in nonlinearity of the model. The larger the weights are, the more nonlinear it's going to be. So weight decay makes the weights small, so it makes the model less complex. This is, intuitive answer to the question. More solid and mathematical question, we'll see it in a minute. Okay. Okay, is that clear what we do in terms of weight decay? Okay. Now let's see more solidly, let's see what's happening in weight decay. Okay, suppose that my objective function is j, and j is a function of theta, my parameter. It's also a function of input, like x and y, target variable. But it's a function of theta. And what I do is to take derivative of this objective function, set it to 0, or use something like gradient descent to minimize this. Do you remember a Taylor expansion? You can expand any function in the neighborhood of any point. So suppose that the solution of the optimal solution of this objective function is W star. Okay? Suppose W star is optimal. Optimal in a sense that it makes this objective function minimum, and it makes the derivative of the objective function equal to 0. What I want to see is that if I add a penalty function here in the form of L2 norm, what's going to happen? What's going to happen to my optimal point? So my optimal point for J is W star. Now I want to see if I add a penalty to J, what's going to happen to my optimal point? My optimal point is going to change, but how does this is going to change actually? So we want to study this. Okay, so this W star is a W star which make the derivative of J equal to 0. Means it's optimal. Okay. Now suppose that I write Taylor expansion of J in the neighborhood of W star. So let me call this J hat. Okay, Taylor expansion of this function is going to be J at point W star. You remember for point F, a function F, at point X star, it's at point A, it's FA plus F prime A over 1 factorial X minus A plus F double prime A 2 factorial X minus A squared plus F triple prime A 3 factorial X minus A cubic and so on, right? That's Taylor expansion. So I will write J at point W star plus derivative of J at W star divided by 1 factorial times W minus W star. But derivative of J at W star is 0, right? So this term is going to be 0 because I assume that I suppose that W star is optimal point. Optimal point is a point which makes the derivative equal to 0. So I don't have this term. Is that clear? That why I don't need this term? No? Yes? Give me a hint that, is it? Okay. Okay, so I don't have that term. The third term is second derivative of the objective function divided by 2 factorial times X minus the point W star squared. So basically it's going to be W minus W star transpose H W minus W transpose. Well, I mean this W transpose, W minus W transpose, and the second derivative, H is Hessian. Suppose that H is Hessian matrix. Okay? And the first derivative I have Jacobian, second I have Hessian. And 1 over 2 factorial. So I just expanded up to here. I don't use the third, fourth, and so on. So with just 3 terms, I expand the objective function. Okay, I used to minimize this. I can minimize this now. This is an estimation or approximation of this function. Okay, so if I look at the derivative of J hat, it's going to be derivative of this term. This term is constant. It's J at a certain point. It's a constant value. So this is going to be 0. Derivative of this term with respect to w is going to be, it's a quadratic form, 2 times 1/2. They cancel each other. So it's quadratic. So it's going to be linear. It's h times w minus w star. That's derivative. Okay. So usually I make this minimum, means I take the derivative of this, or I take the derivative of the approximation of this, set it to 0, that part. If I set this equal to 0, then w is going to be w star. So my optimal w would be w star. But what if I add a penalty function to this? Suppose that I add a penalty function to this. So if I add L2 nor penalty to this, means that L2 nor penalty has been added to this one. And when I take derivative, similar to what we had here, a term of this form will be added. In this case, I'm going to have h w minus w star. That's the derivative of this. And if a penalty term in the form of L2 norm of w has been added to this, then when I take derivative, alpha w will be added to this function. So in this case, this is going to be alpha w. That's the effect of adding a penalty term to the original objective function. That would be the change of my derivative. Now, if I set this equal to 0, what's going to happen? I can write it as hw minus hw star plus alpha w equal to 0. Then hw plus alpha w is equal to hw star. Okay. So let me factor this w. It's going to be h plus I times alpha w is equal to hw star. Okay, when I set this equal to 0, w becomes w star. If I set this one, I mean the regularized form, equal to 0, w would be h plus I alpha inverse times hw star. So the effect is that instead of having the optimum point at w star, my optimum point will be multiplied to this, Hessian plus an identity inverse times Hessian w star. Okay, now let's see what would be the effect of actually multiplying this to w star. So suppose that singular value decomposition of h is u sigma u transpose, or u lambda u transpose. I just do singular value decomposition on h. H is symmetric, so it's going to be u lambda u transpose. So it means that W will be H, for H, I will put just U sigma, U lambda, U transpose, plus I lambda inverse, U lambda, U transpose, W star. Okay. So W will be U is orthonormal matrix. So U transpose U is identity, or U transpose is identity. So I can write this bracket, this form. U lambda plus I alpha inverse U transpose. Inverse. So I just rewrite this bracket, this form, because see, the first term is U lambda U transpose, and the second term is just A is a constant, so it's U I U. This is U. This is identity as well. Okay, I just rewrote this bracket in this form. And then U lambda U transpose W star. So if I apply this inverse to this bracket, W would be, U transpose inverse. This is U lambda plus I alpha inverse U transpose U lambda U transpose W star, which is equal to U lambda plus I alpha inverse U transpose U lambda U transpose W star. This U transpose is identity. So it's equal to U lambda plus I alpha inverse lambda U transpose W star. Okay. This alpha is coefficient of the penalty function. Now imagine that I don't have it. Means that alpha is equal to 0. If alpha is equal to 0, then I have lambda inverse times lambda, which is just identity. And then I have U transpose, which is identity. So it doesn't change W star. So if the coefficient of the penalty function is 0, it has no effect. This will be canceled. U transpose is just a rotation matrix, as if, W star is a vector of your optimal weight. U transpose will rotate it. Then U is the converse of this rotation, the inverse of this rotation. It rotated back. So nothing will change in this case. Okay? Okay, let me, to make it more clear, let me multiply a U transpose from both sides. It is going to be lambda plus alpha I, or I alpha inverse, lambda U transpose W star. Okay. Okay. Now, this lambda has this form. It's because it's a result of a singular value decomposition. It has this form, lambda 1 to lambda n. And you add it with alpha I. So it's going to be alpha, alpha, alpha. And then you take inverse. So, this is going to be like alpha 1, lambda 1 plus alpha, lambda 2 plus alpha, and so on. And when you take inverse, it's 1 over this values. Times lambda, which is lambda 1, lambda 2, and so on. So the whole thing here, it's lambda divided by lambda plus alpha. So a matrix of this form. So again, if alpha is 0, it has no effect. It's going to be 1. But what if alpha is not 0? If alpha is a large value, what's going to happen? What's going to happen if alpha is large? It approaches to 0, right? It's going to knock down the corresponding column of U when one of these becomes 0. So lambda is eigenvalues of Hessian matrix, and alpha is the coefficient of penalty that you add. If lambda I is way bigger than the coefficient, then lambda I plus lambda I over lambda I plus alpha approaches to 1. But if lambda I is way less than alpha, then lambda I over lambda I plus alpha goes to 0. And corresponding column of U will be knocked down. Okay, now this is basically the result. You have a Hessian matrix, okay? Through eigen decomposition, I realized that, okay, this is the eigen decomposition of my Hessian matrix. It has some eigenvalues and eigenvectors. Adding this coefficient, adding this penalty, the effect of adding this penalty is that an eigenvectors of Hessian matrix that has a large eigenvalue, nothing will happen to them. Okay, it approaches to 1, and we keep those columns. But for those eigenvectors of Hessian that have small eigenvalues, that eigenvector will be knocked down. It means my Hessian matrix has like n direction of variations. Adding the penalty function, keep the directions corresponding to large eigenvalues of Hessian, and knock down the directions corresponding to a small eigenvalues. Okay? That's another way of understanding the effect of adding a penalty function. So your Hessian matrix gives many directions of search. But adding this penalty function knock down many of these directions that have small variations and emphasize those that have large variations. So only go to this direction, which is significant. Forget about this small direction. Okay? Is that clear? Is there any question here? So when you design neural network, one way to avoid overfitting is add L2 norm, which is called ridge regression. In terms of computation, it's quite easy. You just need to add one term to your basically update function, update formula. I mean, add alpha times the weight to your update formula. That's it. That's called weight decay, and that's mathematically the effect of this. There's a notion, it's called effective number of parameters. Effective number of parameters is defined by summation of lambda I over lambda I plus alpha. We learned that lambda I over lambda I plus alpha is equal to 1 or close to 1 for large eigenvectors and close to 0 for small eigenvalues. So this summation is basically effective number of parameters. Without penalty, all of them are parameters, but now with adding penalty, many of them have been knocked down. So when you do deep learning or neural network, another way of doing regularization, because it's pretty important to make sure that you don't overfit. Another way of doing regularization is dataset augmentation. Dataset augmentation means that you don't have enough number of data points, you're going to generate some data points. So you have an application that doesn't give you enough number of data points. It's a medical application, for example. You have only 100 patients, and you have 100 data points, but you want to feed a neural network. So the number of data points are not sufficient to learn all of the parameters of neural networks, and you're going to overfeed. Okay? So one way is to augment the data set. How can we augment data set? Create fake data. How can I create fake data? Say, for example, it's images. I can translate images by a couple of pixels to the right, to the left, top, bottom. So I have a digit, I just shifted a little bit to the right, shifted a little bit to the left, and I call it a new data point. I rotate it a little bit. So I can augment data set. That's one way to avoid overfitting. Another way of avoiding overfitting is noise injection. So you're going to add some noise to your input data. So you have n data points, add a little bit of noise to your data. So you can add noise to your data point. You can add noise to weights. When you are learning weights, add a little bit of noise to your weights. There are mathematical justification behind that, which I just skip, with this proof that we had for weight decay. We can prove that adding noise, injecting noise to the input or to the weights have exactly the same effect, will knock down some directions of Hessian matrix. But I will keep it in the slides, but I don't cover it here in class. If you're interested, you can go through the math and see how it works. Another popular way of controlling the complexity of neural network is early stopping. So you basically, early stopping is quite simple. You're minimizing your cost function. It goes down, down, down. So don't go too far, Stop learning the function at some point. So don't go for 1,000 epochs. Go for 500. So you can potentially minimize the training set more, the training error more, by going through more epochs, but don't do it. Stop early. Okay? For early stopping also, you can prove mathematically that it's corresponding to, getting rid of some direction of Hessian, which I ignore here. Another way is parameter sharing. So if I have m nodes here and I have n nodes here, then there's m times n parameters or weights. So I can make some restriction on the structure of this network to make sure that some of these weights are exactly the same. So I want to make sure that these two weights are the same, these two weights are the same. So some weights will be shared or tied together. Later on in this course, you will learn about convolutional neural network, and convolutional neural network, in a sense, or one of the properties of convolutional neural network, that it shares some of the weights. So that's another way of preventing overfitting, by minimizing the number of, or design the training in a way that the number of parameters is less, by making sure that some parameters share the same value. Okay. Another very popular way of preventing overfitting in neural network is an algorithm which is called dropout. So we don't go through the details of dropout now, but dropout basically means that during the learning, you're gonna, in each iteration, you are going to drop half of the nodes randomly. So you have a network and you drop some of these nodes randomly. In next iteration, you drop some other nodes randomly. Okay, so it can be expressed in terms of sparsity, and can be expressed in terms of also ensemble methods. That's why it works. But we'll see this later on. Okay, any question? So for data challenge, next data challenge, for your assignment, you know enough to prevent overfitting if you need to. Okay, early stopping, injection of noise to the input, to the weights, adding L2 norm. You can add L1 norm. So there are many ways, actually. Yes?
Yeah, how do you choose the strength of noise when you add it? Like how much to add?
It's similar to regularization. You can ask that what would be the optimum alpha here, right? We don't know. So yeah, don't go too far for sure. For noise, don't go too far. Don't add too much noise to your data. But there's no good indication of how much noise will be. Any question? Yes?
So the dropout that you mentioned, why would you drop it randomly instead of drop the insignificant ones?
What do you mean by insignificant ones? Well, I mean, it's a pretty good question. No, I'm not saying that it's a bad question. But just I want to make the question more clear, that what do we mean by insignificant? See, when the dropout paper was published, it was sort of hand-waving explanation of why it works, comparing this with brain and so on. But now I think you can explain it mathematically in two directions. One is sparsity. Okay, one way of avoiding complexity is sparsity. Remember that in simple regression, linear regression, you can add L2, which is called regression, right? You can add L1. What is it called? Lasso, right? You can add L1, it's lasso. Lasso makes your parameters sparse. And there are many good properties about this sparsity. There is an unofficial principle. It's by Hasty, bet on sparsity. So in any model, if you can make it sparse, it's better than dense. Even in your daily life, if you can make your life sparse, it's better than dense. Really, beta transpose X is a linear combination of X, right? X is a large vector. d-dimensional. And you have d parameters here. L2 norms make some of them small, or all of them small. L1 norm knock down some of them. So you don't care about this. I'm going to care only about these 3 parameters. Even if in your daily life it's better, you know. It's better to be concerned about 3 things rather than 100 things and do a little bit of this, a little bit of this, a little bit of this, rather than just put aside many of these things. I'm be completely focused, you know. My goal is to be the top student in the University of Waterloo, for example. And is it going to help to be top student in the University of Waterloo? Yes, no. If no, just, or I have a company. Is it going to help making profit in this company? Yes, no. If no, just ignore it. You know, that's what L1 norm does. That's what sparsity does. And has very good properties everywhere. So one way of looking at dropout is sparsity. You know, it adds sparsity to the model by dropping some of these nodes, but it's sort of random sparsity. Another way of looking at this is that it's ensemble method. Ensemble method means an average of some methods that we're going to see at the end of this course, that you can have many classifiers and according to some procedure, take the average, weighted average of the voting of all of them. And you can prove mathematically that it's better. I mean, the worst case would be the error of the worst one. So it's always better than the worst, you know, when you're taking average of others. It's like democracy, you know, when you hear everyone, it's better than just listening to 1%. So we can show that it is ensemble method because in each iteration, you're going to drop some of these. So you're training a new model. This model is different from the model that you learned in the previous iteration because you drop some other nodes that is different from.
Shift to those remaining.
But that's in terms of in the training part. In test part, you don't drop any of these nodes. You keep all of them, but you take the average of nodes that were dropped in the previously, average of the weights. So it's as if you don't have just one model, you have 10 models, but you're taking average of all of these 10 models. So it's sort of bagging. It's sort of ensemble method, you know, that you're taking vote from many models. So that's one of the reasons that it's resistance to overfitting and it works better. But if time allows, we will see the detail of this later on in the course. Any other question? Yes.
For dataset augmentation as well. So I just wonder how to make sure your fake data has the same pattern as the true data for high-dimensional.
The same data has, sorry?
Sorry, the fake data has the similar patterns with the true data.
So we don't do anything very radical, you know, we just shifted, you know, it's images, for example. Say, for example, it's handwritten digits, right? I just shifted 2 pixels to the right, 2 pixels to the left. So it is the same pattern. So I'm not applying a random transformation to this. You know, it's a translation, it's a rotation, something noun, which doesn't change the pattern completely. Okay. Okay. So the next topic of this course is support vector machine. Or SVM. Okay, let's start with a very simple case. And this simple case is the case that we have two classes, and we would like to learn a classifier to make distinction between these two classes. And again, for simplicity, assume that this data is linearly separable. So we learned that we can find a linear function using many methods, including perceptron, for example, right? But perceptron can find many solutions. There's basically infinitely many solutions to this problem. So among these infinitely many solutions, is there a solution that you prefer among all of them? If I can draw many lines here to make distinction between these two sets, is there any of them that you prefer over others? Sorry? Separate them as much as you can. All of them, separate them completely.
Like the points to the line have maximum distance.
Okay, great. So the idea is to find a line which has maximum distance to each of these classes. So this is a solution. Okay? But according to this intuition, this is not a good solution, or this is a solution. This is not a good solution. I mean, it is a solution because it separates them, but it's pretty far from this class, pretty close to this class. So it's the chance of misclassification for this class is high, because I'm talking about training set now. If I show you a point from test set, it's possible that this point, the point from test set is here and get misclassified. But if I find a line which is right at between, has the maximum distance from two classes, then it could be a better solution. More resistance towards misclassification of test points, or to be more technical, a decision boundary with generalized better. Okay? This is also the idea of SVM, support vector machine. In SVM, we are looking for a decision boundary which has maximum margin. So also support vector machine is also called a maximum margin classifier, has maximum distance to classifiers. SVM was state of the art in classification for many years. One of the algorithms that has maybe the most responsibility for at the time that neural network was popular, one of the algorithms that made neural network not popular was support vector machine. It's one of the instances in machine learning that we have great result and great theory. So a very solid theory about the properties of this classifier, solid math about the optimization of this classifier, and very good result in practice. Okay? So in neural network, for example, we have very good result, but we don't have solid theory about what's happening in neural network. But this is one of the cases that we do. Okay, so we are looking for a decision boundary, a linear decision boundary between two classes that has maximum margin. Okay? So what I'm going to talk about is hard margin SVM. Hard margin SVM means SVM for the case that data is linearly separable. Okay? Data is linearly separable. Okay, I assume that my label is either -1 or +1. And as usual, my x's are from RD, and I have n of those. I have xi, yi from 1 to n. So my first task now is to find the margin of this hyperplane. So margin means the distance between this hyperplane and closest point of a data set. So this is basically margin, or this is margin, okay? I need to compute this margin. And then I'm looking for a classifier which maximizes margin, has maximum margin to both class. Okay, in order to compute this margin, let me start begin by looking at the properties of a hyperplane. So we have seen properties of hyperplane when we learned about perceptron. So I'm going to repeat them quickly and add some more to it. So this is my hyperplane. Beta transpose x plus beta null equal to 0 is my hyperplane. So we learned that beta is orthogonal to the direction of hyperplane. So if I take 2 points x1 and x2 on the hyperplane, so beta transpose x1 plus beta null is equal to beta transpose x2 plus beta null, and is equal to 0. Because both of these 2 points are on the hyperplane. So it means that beta transpose x1 is equal to, minus beta transpose x2 is equal to 0. And it means that beta transpose x1 minus x2 is 0. It means that beta transpose is orthogonal to x1 minus x2. So beta is orthogonal to hyperplane. Okay. Okay, the second property is that for any point x null, beta transpose x null plus beta null is equal to 0. And this means that beta null is equal to minus beta transpose x null. So we also learned that if I want to find the distance of a point x, this point, if I want to find the distance of this point to the hyperplane, I can choose any point x null on the hyperplane and find x minus x bar, and then project everything on beta. That's going to be the distance. We learned this in hyperplane, in perceptron. So the distance, to compute distance of x to the hyperplane, I can compute x minus x null projected to direction of beta. But I need to normalize it as well. Okay. Beta with norm 1. So this is beta transpose x minus beta transpose x null over beta. Beta transpose x null is beta null. So this is beta transpose x plus beta null over beta. Okay, this is distance from hyperplane. Let me call it d. This is basically sign distance. Remember from perceptron, if on one side of the hyperplane it's positive, on the other side it's negative. Okay, so distance would be di times yi. Distance 4 point xi would be di times yi. So on this negative side, plus times negative 1 becomes positive. On the positive side, times positive 1 becomes positive. Okay. So is it clear so far? I didn't spend time on it because we had it in perceptron. Okay, now what is margin? Margin is the distance of the hyperplane to the closest point, right? So distance of points to the hyperplane is diyi. So among all diyis, which are distance of all points to the hyperplane, if I look at for the one which has the minimum value, that would be my margin, right? So margin would be minimum of yi di. Because yi di is the distance of a point to the hyperplane. Between all points, the one which has minimum distance to the hyperplane, that's margin. Right? Clear? Okay. So now I need to find this margin. So margin is minimum of yi times di, but I know this is di. So it's yi times beta transpose xi plus beta null divided by the norm of beta. Okay, now I'm going to say that points are either on the hyperplane, in this case beta transpose x plus beta null is equal to 0, or off the hyperplane. In this case beta transpose x plus beta null is greater than 0. It's not equal to 0. So I'm going to say that for any point that is not on the plane, hyperplane, yi times beta transpose xi plus beta null is greater than 0. Do you believe? Because if it's equal to 0, it is on the hyperplane. If it's off, if it's not on the hyperplane, it's greater than 0. It's not equal to 0. So if yi times beta transpose xi plus beta null is greater than 0, it means that it means that yi times beta transpose xi plus beta null is greater than equal c. It's greater than 0. That I'm sure. It can't be equal to 0. It's greater than 0. So there is a number c such that it's either greater than c or is equal to c. See, this point is not on the hyperplane. It's here. So it's greater than 0. So for sure there is a number c such that it's greater than equal c. So it's far from hyperplane by c because it's not on the hyperplane. So do you agree with this? Okay, now let me divide both sides by c. So yi times beta transpose over cxi plus beta null over c is greater than equal 1. What's the effect of dividing beta by c? Beta is a vector. When I divide it by c, it doesn't change the direction of the vector, right? It just changes the length of this vector. So let me call it beta star. So there is beta star transpose xi plus beta null star such that for all points it's greater than equal 1. So you know what it means? It means that for any hyperplane, I can rescale beta and beta null in a way that all points, the distance of all points from the hyperplane is 1 at least. So here I know that the distance of any point from hyperplane is at least c. What I'm saying is that I can change beta in a way such that the distance of any point from hyperplane is 1. Okay? So if the distance of all points from hyperplane is 1, at least, so the closest point is 1, right? Look at this definition of margin. Margin is minimum of this quantity divided by the norm of beta. Now I'm claiming that I can rescale beta in a way that this is at least 1. Could be larger than 1, but cannot be less than 1. Okay? So in this case, if I want to minimize this, and I know the minimum value of this quantity is 1, so I can just replace this by 1. I mean, since I can rescale this, I just write it beta, means there exists some beta. And beta null such that yi times beta transpose x plus beta null is greater than equal 1 for any point for all xi. So I can replace this by 1 because this is the smallest value. It can be less than this. So I have 1 over beta. If I want to minimize this quantity, this should be a small, this should be large. If you fix a hyperplane, give me a hyperplane with these properties, then this is at least 1. I would put it here. So the margin would depend only on beta. So that's going to be my margin. So if I constrain my hyperplane to have a beta such that the closest point to the hyperplane has at least 1, as a distance is at least 1 unit apart, then that's my margin. Now I want to maximize margin. I can form an optimization problem in this form. My margin is 1 over the norm of beta. Maximizing margin means maximizing this beta, the norm of beta. Okay? So I can form an optimization problem in this form. Maximize norm of beta subject to the constraint that this beta is beta of a hyperplane such that for all i's, yi times beta transpose xi plus beta null is greater than equal 1. Because we computed the margin under this condition, that we rescale beta in a way that this condition holds, right? Under this condition, 1 over beta is my margin. I want to maximize margin. I want to find a hyperplane which has maximum margin from each class. To maximize margin, I have to maximize this beta. I have to minimize this beta because it's going to maximize the margin, right? Minimize the denominator in order to maximize the whole fraction. So which norm, I'm going to use norm 2. So, yes?
Are we still trying to find the margin right now?
No, we have the margin.
That, okay.
1 over beta is the margin. Yep.
And now we're trying to find the SVM.
We are trying to find SVM. So when you have the margin, so far, up to that point, my goal was to find margin. And I realized the margin is 1 over beta for those hyperplanes that satisfy this condition. Okay. Now I'm saying that, okay, for those hyperplanes that satisfy this condition, that's my constraint. I'm looking for the one which has maximum beta norm. That's the one which is further apart from all. Okay. So in the next lecture, I'm going to show you how we can solve this problem and how we can find beta. Any question? Okay. See you on Thursday.